So again, I have a merry-go-round, and it is got a radius of 2 meters and has a mass of 200 kilograms. There is a kid standing on the edge, and he has a mass of 50 kilograms. He has a point mass. I'm saying this because that should trigger in you how to deal with their moments of inertia. So when I say that the merry-go-round is a disk, that should conjure up, well, I know that's 1/2 mr squared. And the point mass might be harder for you to remember, but the moment of inertia of a point mass is mx squared, where x is how far away from the pivot point they are. So they're at the edge. So I would say that they're 2 meters away from the pivot point. That all good? So do me a favor, and could you take a moment and calculate the moment of inertia of the system? That'd be adding those things together. And I'll wait patiently. What it was. We have the top one plus the bottom one is how many? 600 kilograms meters squared. All right. So let's say that the kid, just before he got on there, or maybe he's on there and he's got his leg off and he's pushing on it, right? You can imagine different ways he would have gotten this thing spinning. Let's say he got it spinning so that it is now spinning at, let's go with 6 radians per second. Okay, that's not particularly fast. It's about 2 rotations per second. So maybe kind of fast, but we'll just pick a number. That's how fast it's going. I already gave it to you in radians per second. You don't have to convert anything. Based on what we talked about already, you should be able to tell me the angular momentum of the system, because angular momentum is just I times omega, right? The system has momentum because it's spinning. This, remember, it's inertia while moving. So once you get something spinning, it's going to want to stay spinning because it has angular momentum. So for the case of this problem, we have 600 kilogram meter squared worth of moment of inertia times 3 radians per second of spin, bringing our grand total for our angular momentum to 1,800 kilograms meter squared per second. It's an odd unit. Yeah. True. I said 6, not 3. So, good call. So, double that to 3,600. There we go. Kilograms meter squared per second. It's a weird unit. And I don't want to have too much of a side note here, or side channel conversation, but so not including anything that was radians per second, 9 different combinations of kilograms, meters, and seconds so far this year. And all of them with a different name or a different meaning. Oh, you gotta be kidding. Just so silly. All right, so here's the thing. This is the important part, the part that has physics involved. We did all of this. This is no big deal. To me, this is straightforward. If you want to calculate something's angular momentum, you need to first find its moment of inertia, and then you just multiply by the speed. It's pretty straightforward. Just keep in mind, this is our units. Now, I want to talk about what happens when the kid decides they want to walk towards the center. They're changing the moment of inertia of the system. However, there's no external torque on the system. There's nothing on the outside of this system that is changing the speed or the rate that the thing is spinning. No external torques, right? So under these circumstances, if there's no external torque, the moment of inertia and the angular speed are still the angular momentum. Without any external torque, the angular momentum remains unchanged. It's like collisions, where if there's no external force, the momentum of the system stays the same. This is the case that there's no external torque, the angular momentum of the system stays the same. But the difference is, with linear objects, we didn't talk about problems where they change their inertia. Like we didn't talk about rockets, which burn off most of their mass. But in this problem, the kid walking to the center changes something about the system. So here's our merry-go-round. It's spinning. But the kid is now standing, say, here. Half a meter from the center. First question, how does that change the moment of inertia of the system? Did anything about the disk change? No. What did change? Go ahead. The axis changed, right. So although the disk is going to stay the same, that was 200, right? We need to find out by how much the kid's moment of inertia changed. Take a minute, find that out for me. What? It was 400, not 200, Mr. Shelton. Come on. The kid, he's now closer to the center, right? Can you mash those numbers together real quick? What's that? 12.5. For a grand total of 412.5 kilograms meters squared. Now again, this is important. The angular momentum doesn't change, but the moment of inertia changed. So we still have an angular momentum of 3,600 kilograms meters squared per second. But now the moment of inertia is 412.5. What's our new angular speed? Let's do a little bit of simple division. Go ahead. 8.7 radians per second. So, kid walks towards the center, whole system speeds up. You guys see that all right? I start in a circle like this, start spinning with my arms out, pull my arms in, whole system speeds up. So, this is a typical angular momentum question in which there's no collision, but there's a clear change in the motion of the object. So let's big picture for a minute. If an object is experiencing no external torque, I'm giving you the things you have to be able to say. If an object is experiencing no external torque, its angular momentum stays the same. If an object is experiencing no external torque, then its angular momentum stays the same. So the angular momentum before its shape changes has to equal its angular momentum after its shape changes. In this case, it's the moment of inertia of the system before its shape changes times its speed before its shape changes. That has to equal the moment of inertia after its shape changes times its speed after its shape changes. I know it's pretty obvious, but if the moment of inertia increases, the angular speed has to decrease. If the moment of inertia decreases, the angular speed has to increase. The product has to stay the same. In the problem we just did, the moment of inertia decreased because the kid walked towards the center. But that made the whole thing go faster. Now, that part seems pretty clear. This is where it starts to get a little muddy. Do me a favor, because everything you need is sitting here on the screen. Calculate the kinetic energy before and the kinetic energy after. Are you guys done yet? I need you to see something because it's important that you see this. So how much energy did we have before? 10,000 what? 10,800 joules of energy. And then how much energy did we have after? 15,000 what? Joules of energy. That's not what you got? It's close. Do we need to do this? Like, okay. The momentum stayed the same. I want to point out something. Whenever we did collisions before, do you remember how always the energy went down? Almost every time? You see this, right? I'm putting it right out. Where'd the energy come from? You see that the energy increased, right? The energy had to come from somewhere. It came from the kid. The kid did work walking to the center. Positive work. I'm going to ask you on your next quiz, did the energy of the system increase or decrease? The way to find the answer out is to calculate the energy before and the energy after. If the number is bigger after, the energy increased. But I'm not going to ask the question that way. I'm going to say to you, how much work was done on the system? And I'm asking for, by how much did the energy change? I'm telling you the code. I'm sending you a coded message. You want to get it right? Break the code. Here it is. I'm going to ask you how much work was done on the system. And the answer is going to be, what is the change in kinetic energy of the system? This system increases its energy. It has to get that energy from somewhere. It got it from the kid. And the reason the kid was able to do this is because they were able to fight the force trying to fling them off. Right? If you're on the merry-go-round, you feel as though you're being flung off. You're not. It's your inertia wanting to travel in a straight line. And it requires an unbalanced force to get you to go this direction. So there has to be a force towards the center of the circle. It's you holding on. You're causing this force so that you don't get flung off. It's the friction between your feet and the ground. Right? There's usually a bar like right here. And you're holding on to that bar. And if you want to go to the center, you have to work against that force. You have to push yourself against that force. When I'm up here standing on that thing and I'm spinning in a circle, I have to pull my arms in against their natural desire to stay flung outwards. Who's been